ChemPlus 2022. Today, right now, we have Dr. Vijaysai P, who heads the L&T Water Technology Center at L&T. I'll give a brief introduction of him. He heads the Water Technology Center, which is the hub of R&D digital knowledge management for L&T Water and Effluent Treatment business. He has over 25 years of experience in industrial research, commercialization, digital strategic positioning, and crafting productized services. As a chemical engineer by training, Dr. Vijaysai completed his Ph.D. in System Identification and Control from IIT Bombay. After a few years of service in academia and a short stint at National University of Singapore, he joined Automation Group of Global Research Center of GE in Bangalore and worked on technology development for several industrial segments of GE, which included renewables, transportation, consumers, and industrial oil and gas. Dr. Vijaysai joined Technology Division of GE Water and Process Technology business after an internal role and took roles in increasing responsibilities within GE Water business. He led the South Asia technology team for GE Water and led the digital initiatives for business globally. After the divestiture of GE Water business, Vijaysai moved to L&T in May 2020. He has over 27 patents filed, with 8 granted by USPTO as the lead inventor. Vijaysai is quite passionate to collaborate with academia and recently mentored 5 PhD scholars of IIT under our Connect program. He also guides and works with researchers from other IITs in water and digital wastewater treatment, hydrocarbon processing, and advanced analytics, are his key area of interest. Sir, now you can, over to you and you can start your lecture and presentation.
Sure, yeah. Thanks, Manichandana. Hope I am audible now. Okay, great. Yeah, first of all, a very warm welcome and a good morning to all. It's a great, bright day today. I would like to specifically thank Professor Raj for having invited me to this lecture series. And of course, thanks to Manichandana for coordinating it so well. So today I'm going to talk about the water particularly, and the topic, as you all know, is clean water nowhere. Depends how do we use this very popular word nowhere. It is whether it is nowhere or now here. It depends on the context, and we will understand the significance of it as we move through the presentation. So let me just see if I can share my screen now. Yeah. Hope
it's visible.
Okay, great. Thanks for that. So I just wanted to, in fact, talk about the way this talk is organized, and the choice is up to the coordinators. How do we want to, have this presentation going? There could be questions in between, or probably we can take it towards the end. I will try to wrap it within 40 minutes, but if there are any questions in between, definitely we can take that too. So I will leave that choice to the audience and the coordinators here. So coming to the topic, the way I have organized this presentation, I call it as the law of the land, just an overview. And why it is law, we will come to that very soon. So then we have a very interesting situation today, what we call as the game of the progress versus protect, so with the science being the driver over there. So how do we look that aspect as well? When it comes to water as the domain, and that water being part of the environment. So technologies for water treatment and the role of chemical engineers, that will be the next topic. So I would like to talk about a product that L&T Water has come out with, which is AGBR, and how did one go about, improving, developing, and then demonstrating application of this product is one thing that I wanted to take it today so that it benefits everyone here. Finally, we will conclude the talk, and this is the way it has been organized. Interestingly, I call it as the science of sacred 7. It's a coincidence that science is also a 7-letter word. However, the sacred part is something that is associated with our mythology here. So way back, in 5,000 years, even more, we knew that, the light is made of 7 colors. We call it as a Saptashva or Ratha Saptami. And, we talk about the 7 chakras or the 7 spiritual centers in the body, which are associated with the ductless glands. Likewise, we also talk about the 7 world or the lokas associated with the 7 ocean. There are the 7, and the list goes on. It is associated with even the notes in the music, which is the Saptaswara. But the question here is what it has to do with the topic that we are talking today and how it is connected at all. There is some connection, of course. And of course, we have talked about the 7 sacred cities and the 7 holy rivers of our country. If we in fact look into the map that we have here, so we have called Ayodhya, Madhura, Maya, which is Haridwar today, and then Kashi, which is Varanasi, then Kanchi, which is nothing but Kanchipuram, and of course Ujjain and Dwarka. We called it earlier as a Dwaravati. So those were the 7 cities that were considered to be the holiest places in the country. Likewise, we have marked the 7 rivers too. So Ganga, Yamuna, Godavari, Saraswati, Narmada, Sindhu, Kaveri. These were the 7 holy rivers that we perceived in our literature in way back 5,000 years and even a few thousand years too. So coming to that, what is the significance of that in the today's context? Is that how do we think we have transformed this all land, water, air in the today's context? In fact, the yogic literature as well talks about the 49 types of the vayu or the air in our body, which is also a derivative of 7. But in the today's context, the 7 topmost polluted cities in the world are in India. And that is quite contradictory to what we had seen in terms of the significance we had assigned to few places in the past. 70% of our water body today have been declared to be polluted, and the 6 rivers are in the worrisome state now, and one of course is being reborn, which we call it as Saraswati. Now, the land degradation has become a major issue, and we should realize that 70% of the land is left now, from being degraded, which we have to pay attention to now. So there is quite a lot of, things that are happening to land, air, and water. And that is what I, in fact, want to call it as the law of our country, which is quite significantly damaged. So when we say that these are all damaged, we try to look at the factor. Is it the population? Is it the education? Is it the the poverty? What is that actually has led to this degradation? And some people, in fact, ascribe it to science as well. So maybe the science is one of the factors which has contributed to all these things. Is that the way to look into that? I mean, if science is responsible, let's look at what science has done to our life, and let's not belittle the the importance of science in our life today. We have seen virtual presence, which has made the distance almost meaningless today in terms of connectivity, what we enjoy. We have amazing tall structures. They are tall to the extent that they are the ladders to the cloud and even beyond. And the structural engineering marvel we have witnessed, which has never been even dreamt a century back. Circumnavigating the Earth might today take a little longer time than reaching once a mysterious Mars. And that's the space mission, what we have achieved. There is a situation today where, in fact, the pets have started envying robots. Very soon, they will start getting confused. Who is my owner too? So that's also a robotics that has taken to a different level. Let's think about automation now, where the steering of the car, in fact, is questioning the role of a driver. Sit tight and sit idle. Let me do the job is what the steering is telling to the driver. So the life is filled with so much of excitement. It's enjoyable, and it has made our whole Earth smaller than it used to be once. So this is all due to the way engineers have crafted this, and there is a rich excitement in everyone's life today, and that's exactly what the science and technology has brought to our life, and thanks to the role of engineers here. And as we look into the near future, it's even more exciting. We be it in terms of academia, pedagogy, medicines, healthcare, cyber security, cyberspace, cyber world, and then virtual reality, and then the list goes on. And even in the energy segment, whether it is the new fusion concept that's coming out, and the list goes on here. And the world definitely is going to be more exciting, more enriching, more enjoyable as the time goes with the science and technology that we are getting to see. Very interestingly, we got to look into how this whole development has happened over a period of time. When we talk about nomadic to agricultural era, it happened over a millennia. And when we talk about agricultural to industrial era, it took mostly centuries. Then when we talk about industrial to information era, which in fact we are now, it happened in decades now. So what is the next phase that we are going to be? That's where we call it as a sustainable era. We have achieved this far, but then we got to kind of bring in the sustainable wave also into this equation. So how are we going to achieve it? What are the ways that we can probably remain sustainable in this environment? So that's where the things become in fact more concerning now, because when we look into the land, these are the quick statistics which we can immediately pull out from our internet. The solid waste is reaching an alarming level. The health hazard associated with solid waste is growing day by day. Leachate has become a problem, and every year we have been dumping enormous amount of solid into the ocean here. When we talk about air, in fact, it is affecting our GDP in some sense, and then our productivity, in fact, is getting affected, and also the agricultural yield is going down. In terms of pollution impact, we are seeing that 7% of our healthcare funding is getting lost because of the air pollution. And India, in fact, tops the list, whereas around 1.8 million people die every year because of the air-related issues. Most importantly, in today's context, what we are seeing in water, and the data is no different. There are innumerable waterborne diseases that we are getting to see because of the polluted water bodies. As I said, 70% of our water bodies are polluted in the country, and 50% of the rivers, we have said, are already polluted here. So we got to, in fact, now understand the context here. On one end, the science and technology has helped us progress and then make this world so beautiful. On the other hand, the same science and technology has led to all these miseries here. What is then the solution ahead? So the solution is very simple. It is like to use the same science and technology to correct what you have created. And that focus now has to slightly shift. We have progressed all along on the progress part. We have focused more on the progress part. Now the shift has to be towards the protect part. And then definitely the world will come back to where it was, and we will be able to retain the lost glory in terms of the purity of the land, air, and water. The law will be protected here. So that's essentially what I wanted to set the context here. And basically, if we have to quote the American astronomer here, the Carl Sagan. So he says that we don't inherit the earth from our ancestors, but we borrow it from our future generation, and which is a very loaded statement. And the responsibility and the onus lies on us in terms of protecting it and making it even much cleaner, more beautiful for our future generation to enjoy this. We moving on to the particular topic of water now. So I definitely land, air, and other things we can talk about later, but the focus today is going to be water, and then how are we going to manage all the challenges that are associated with water. So when we talk about that, it's important to understand that what constitutes water, what makes water, what do we mean by impurities? What is the cleaning that is associated with that? And particularly, what is the role of the chemical engineer? So I would say that, in terms of water, these are the basic, ingredients that you can consider to be the water. And then if we understand these three parameters, particularly the organics, solids, nutrients that are there in the water, interplay between them, I think we have understood water completely. But the fact here is that the interplay is so complex and so tightly linked that sometimes it becomes almost impossible to decouple them and understand the water in totality. But however, when we talk about organics, it is the parameters like COD, BOD, TOC, which typically is a parameter as fundamental as current and voltage for electrical engineers. So whenever you talk to people in water domain, these are the parameters which they, in fact, the COD and BOD particularly, they talk very often, and try to link it with the quality of water, and try to understand the quality of the water they are trying to treat. Likewise, when we talk about solids, we all know that TDS refers to the dissolved solids, and suspended solids is DSS, and volatile suspended solids is another part of the dissolved solids here. And when it comes to nutrients, which also have to be removed in the water to be considered it to be clean, we have totals at all, nitrogen, nitrates, and total phosphates, and these are the impurities here. Of course, there are physical properties like pH, temperature, humidity, color, odor, and all these things are the physical properties. So, when we think about treating water, the importance of all these parameters should be known, and then we can finally say that how this water can be treated and what's the technology to be used for treating this water. So typically, when we look into water as a business, we look into the three segments in particular. We talk about drinking water, we talk about sewage water, and industrial discharge, what we call effluent treatment. So in sewage and effluent, I broadly put them under wastewater category, and drinking water, of course, is something which is coming from various sources, which is subjected to some level of treatment, and it is made available for the users to drink. Of course, there are packaged drinking waters, there is the natural mineral drinking water, and then the water what we get from our tap, which is supplied by the municipalities or the corporation. So today, all water situation is not, considered to be safe, because even when you think about the drinking water, there are so many impurities that are present in the dissolved and suspended levels in water. It could be arsenic, it could be lead, it could be fluoride, it could be, even to the extent uranium. Just Google uranium levels in Indian water. You can see almost the whole country is painted in red today. And the World Health Organization recommends 30 ppb as the safe level of uranium in water. But then majority of the states, out of 1,477 the samples that probably what has been tested, the uranium level has gone way above the prescribed limits. So that is due to various reasons, of course, which we can look at the later point. So there are various standards, in fact, the country uses. In the standards that are prescribed for India condition is even some of the parameters are stricter and more stringent than the European standards. But then the whole challenge here is how do we implement for the scale of economy what we have, the population we have, the infrastructure we have. That's where we got to come forward and then figure out the right solution to make this water potable and usable with no hesitation. So there are treatments that are being followed today, which are mainly physicochemical. And when we talk about sewage water treatment, it is a physicochemical, biological, and disinfection, advanced oxidation process. Now, we will come to that very shortly. What do they actually mean? And when we talk about the effluent treatment, which is particularly industrial, this is a suite of hybrid technologies. Not just one technology can solve the kind of impurities that are there in the industrial water. It could be physicochemical, biological, thermal, whatever you call it as. So what are these techniques? We can quickly look at the chart what we have in front of us now. So when we think about the chemical ways of treating water, we can do about the foam control. Bioaugmentation is another technique. Coagulants and flocculants we typically add to water to settle certain suspended impurities. Physicochemical treatments are the barriers, plus the chemical treatments which we kind of introduce here. So you are very familiar with the sand filters and the multimedia filters that are typically used to clean the water. Likewise, we can think about the clarifiers, thickeners, and all as part of the physicochemical solution. Now, physical solution, we can call it as the absolute barriers what we create. It could be membranes and separators and things like that. There are techniques out now to take out the dissolved solids in water and certain organics in water, which are electrochemical based now. And likewise, thermal is a technique where we just boil the water even under the vacuum or atmospheric conditions, so that we get the cleaner water as the vapor, and the mug gets left out. So that's the thermal solution. And today, that's why I have highlighted it in a different color. We are focusing more on the biological ways of treating water. And let's keep the focus today for the biological treatment techniques, and then how this will be helping us, particularly to address the situation of municipal wastewater. Before we get further into the topic, I just wanted to take a small pause and understand if there are any questions, or we can move forward.
So
Okay.
there seem to be no questions until now. We can.
Okay, thank you. So when it comes to biological means of treating water, and what does actually it mean? This is a typical aerobic process, what I am trying to show here. What is the aerobic process? The aerobic process is where we are supplying oxygen to the water. And what is the need of oxygen? There are microorganisms that we want to specifically grow in the wastewater which is to be treated. Why microorganisms? Because these microorganisms survive on the waste that this water carries. So basically, if you look at the organics or the waste, what we call that are part of the water, so they are it's shown as the square box here. The bacteria is the one which is actually suspended in the water here. Typically, this bacteria lives on oxygen, so that's why there is a air that is being supplied. Now, how does this happen? We can probably look through the slide here. So we are continuously blowing air. So in the presence of air, the oxygen reaches the microorganisms. The microorganisms eat this, food, and that food essentially serves as what we call as a substrate, as the main source of food for the microorganisms, these impurities. And the microorganisms grow. They finally die, and when they die, we call that whatever the dead mass as the sludge. That has come out of the treatment. So that is the way in which the wastewater treatment happens in the biological context here. So what are we trying to remove in terms of wastewater? We have the carbon as the main source of food for the bacteria. So we are supplying oxygen through the air. So basically, the carbon oxygen react to form the carbon dioxide and water in the presence of the microbial action. So that's what we call it as a treatment here. Likewise, there are nutrients in water. The nutrient could be ammonia or phosphate, and the ammonia basically gets converted into nitrite, nitrate, and finally the nitrogen. And that is also a biological process. And in the presence of bacteria, this whole process takes place. So this is all very fundamental to the water treatment here. We will be, in fact, touching upon many terminologies here. For instance, there will be biological oxygen demand and the chemical oxygen demand. So in a sense that we know that the wastewater comprises organics, which we consider to be part of the waste. Now, the organics are nothing but the carbon compounds. Now, the carbon has to be converted to CO2 in the presence of microorganisms. So, if we are talking about the amount of oxygen that is required to chemically convert this carbon source into CO2, that is, what is the mass of oxygen required per liter of this particular waste? We call it as a chemical oxygen demand. That is the COD, which is most fundamental. So that is nothing but the mass of oxygen that is required to act on the organics in the water and then convert it into CO2. Likewise, we talk about the biological oxygen demand. So basically, how much of oxygen is required for the biology or the microorganisms that are present in the water to convert this waste into the organics into the CO2. That is the biological oxygen demand. Because as you can see, what is chemically convertible need not be amenable to bacterial action. So that is where the BOD mostly will be less than the COD in the wastewater context. So those are the important terms which we can probably remember. Suspended growth systems are the one where the microorganisms that I showed in the previous animation are suspended in water, so they are free to move and they are free to chew up this particular impurity that is coming in. And attached growth systems are the one where these microorganisms are basically glued or attached to a particular surface, and the impurities basically reach them, and then they basically get subjected to further degradation. So that is what is the attached growth process. Nutrient removal, biological nutrient removal refers to the removal of nitrogen and phosphorus in the wastewater. Likewise, we divide the treatment process into two, aerobic and anaerobic. Now, aerobic is the one where we supply oxygen through the air or direct oxygen, and anaerobic is the process where we treat the whole water in the absence of air, and we strictly remove the air from the reactor, and we help the anaerobic condition to prevail there, and then the further degradation to happen through the anaerobic microorganisms. Anoxic process is something where a very small amount of oxygen will be present in the system, and unlike aerobic and anaerobic, where anoxic is in the absence of or the very small presence of oxygen, this whole reaction would take place. So like that, the one technology that was extensively used until now, I know it started with the 1914, in fact, is called as the activated sludge process. So what essentially happened in the case of activated sludge process is that, it's a very, very interesting concept here. So you have anoxic section to begin with. As I said, this is for the removal of all the nutrients, and we have aerobic section here. So in the aerobic section, we blow air and the bacteria grow in the tank. In the suspended growth mechanism is there. The bacteria eat the incoming organics or the food that they are supposed to be using. Finally, the organics get converted into CO2 and water. And whatever the bacteria that you are able to separate out from the water is essentially taken to the clarifier. The clarifier is nothing but the settler here. It's a huge tank that is designed to allow the bacteria to settle down. They settle, and then you remove the excess bacteria as the sludge, and the remaining bacteria, you send it back to the anoxic tank. In the anoxic tank, what's essentially happening is the ammonia in the water is getting converted into nitrate in the presence of oxygen. The same nitrate is getting converted into nitrate in the anoxic section because it's a kind of a reducing environment. This aerobic section is an oxidizing environment. So that's a basic chemistry which we all understand. So hence the nitrate gets converted into nitrogen, ammonia gets converted into nitrate in the aerobic section, and the carbon gets converted to CO2 in the aerobic section. So this is all what happens for the wastewater treatment in the aerobic environment here. Now, the advancements have started happening later in 1970s, 80s, and people, in fact, started further improving what you call as the process intensification. Now, could I be able to achieve the same output or better output by reducing the footprint, by doing certain changes to the process, how I can squeeze the process to give me more? output. And that is the effort which started. And with the availability of better membranes, the membrane bioreactor then started becoming more popular. What happened? Because I told that whatever the clarifier that we are considering there are the huge structures there. Why do we need to construct a very huge clarifier? Because all the suspended microorganisms, once they slip from aerobic section to the clarifier zone, they got to settle due to gravity. Now that is where like large amount of time and the volume is required for the bacteria to settle down, and only the clean water can basically overflow, which we call it as the treated effluent here. So whatever the bacteria that get collected here are sent back. But is it an absolute barrier for the bacteria to be retained? The answer is no. That absolute barrier was the membrane bioreactor. So you introduced an ultrafiltration membrane instead of a clarifier. That's the only change that has happened. Now, this ultrafiltration has a very fine pore size, which basically became an absolute barrier for the bacteria to slip through. And it only allowed the clean water to go out. So that way you could separate clean water from the bacteria. And what you did with the bacteria, the whatever were rejected were sent back again. And by that, the bacterial concentration in the aerobic and anoxic section could be increased significantly, by which you could have your treatment efficiency going up multifold. So essentially what we did, so we created a barrier through the membrane, and we increased the concentration of the bacteria. But membrane bioreactor today is also a choice in the many developing countries, has many challenges too, because of ultrafiltration introduction, your capex and opex go up significantly. And the operating expenses are because you need to spend enough energy to clean the membranes clean, or keep the membranes clean. Basically, there is a scouring to remove the deposits on the surface. There is a back pulsing that happens from the surface. So there are multiple things which we have to do to kind of achieve this. So that's where the capex go up and the opex go up. But the cost of the membrane replacement sometimes are quite high. Requires experienced operators to make the things work. So finally, the adoption or the reuse for the discharge is a good one, because the quality of the water that comes out is quite clean. But at the same time, we got to be mindful about the opex and the capex part in case of MBR. So the next change that happened is what you call as the MBBR. And in the MBBR context, we introduced some kind of a packing material into the system here. So there is these packing materials act as a surface for the bacteria to come and sit on the surface, and then remain suspended within the water environment, wastewater environment, so that they can chew up the incoming organics with the growth of the biofilm that is happening on the surface of these packings. So that is the next change which MBBR brought in. And definitely, MBBR was a successful technique in majority of the cases. And there was a modification to MBR later on, which we called as the integrated fixed film activated sludge, where you basically, instead of letting the sludge go out after the clarification, you basically use the same activated sludge concept, where you bring in back some amount of sludge from the clarifier and use it in a recycle mode, which is called as the integrated fixed film activated sludge process. So the big change that I want you to notice here is the attached growth mechanism that we kind of leveraged here with the help of the packings, because the bacteria mobility in the suspended growth is quite intense, but there are other drawbacks too. But the bigger advantage for the bacterial to get suspended over the attached growth is that there will not be much loss of the bacteria with the effluent that is leaving the tank. They remain attached to the surface, and with the surface they will be able to treat the wastewater effectively. Now, with all these developments that happened, I just wanted to touch the last kind of a reactor here, because all these things are very much necessary to understand the next topic that we will be quickly covering, which is called as the sequential batch reactor. This is a beautiful concept which got introduced of late, and particularly this is the most widely used concept in our country, in India. Why? Because we kind of exploited a lot of other benefits in the wastewater treatment through this technology. So what essentially it does is it's a batch process. It allows the sewage to come and fill into a tank. It's just a one tank instead of like having all those previous tanks, for one for membrane, one for aerobic, one for anoxic and other things. So it fills in the tank, and it reacts in the tank in the presence of air. So after we blow air for some time, we shut down the airflow. Now naturally, now it became anoxic and anaerobic environment for you. And in that anaerobic environment or anoxic environment, you allow the sludge to settle down, and this will basically give you enough time for the denitrification to happen. And then you decant the clean water, and then you can take the whole process back into the cycle, and again you start filling the sludge. So basically the react, settle, decant, these are the important steps that got introduced into the batch reactor. The biggest advantage of this technology is this is simple. This requires only a single tank, and you don't have to go for expensive pumps, and the energy wise it's quite efficient. And for a cost conscious market like India, this worked pretty good. And most of our sewage treatment plants today are using the SBR as the technology. So what is important for the Indian context? See, we cannot afford a technology that is quite expensive in the CapEx and the OpEx front, because the operational expenses are concerned for the country like India. So we cannot allow the technology that demands huge amount of energy. We shouldn't allow a technology that consumes huge amount of land, or the footprint is quite significant there. Also, if the technology is producing a lot of sludge, particularly this dead biomass, then taking that sludge out from the premises is going to be a challenge. If the technology demands quite amount of the chemical to be added, and the sludge accordingly generated from these chemicals, that's also a concern for a country like India. So what do we need essentially for a country like India is the technology that consumes lesser power, lesser footprint, lesser generation of sludge, and also lesser chemicals for treatment of waste. So how do we basically move to the requirement that our country particularly has? Is the solution that we came up in L&T, which I am going to quickly touch upon, and then see how this whole effort was carried through, and how this whole exercise essentially gave us a product which is quite differentiated today in the market, and in the context that what the country needs. So that is what is basically called as the AGBR technology, that is attached growth bioreactor technology. And if you see the sewage water treatment process that we essentially were talking all along, so basically this is a floating material or grit removal mechanism what we have in the beginning. Then we have a primary solid removal for the sewage water that comes in. Now the heart of the system is basically a secondary process, which I talked earlier as the aerobic activated sludge process. And then we have the water going into the sand filter. Finally, it's coming with the tertiary treatment as a treated water. So now the heart of the system, which is basically the secondary biological treatment system, we introduced what we call as the AGBR, which is in fact the blend of attached growth and the suspended growth technology. So this is what we call it as the hybrid technology. So what it essentially does is that it took the moving bed bioreactor concept, or the fixed film bioreactor as the concept, and then it integrated with the concept of the sequential bioreactor and the activated sludge process. So this is a hybrid system. Now how does it work? There is a lot of work that happened in the lab, and the systematic development process was undertaken. So when we looked into the lab scale studies, we basically spent quite a lot of time in terms of understanding the design and fabrication that is required to select various media that are relevant from the attached growth perspective. Because in the MBBR case, we have seen those granules, how they provide the surface for attachment of the bacteria. Likewise, what are the other media that we can essentially think for growing this bacteria on the surface and creating this attached film on the surface of the media? So there are a lot of media were tested tested, and the performance and the best media selection essentially happened through the lab studies, and the chosen media essentially was tried in the pilot scale, and then we recommended what is the best media to go for this particular technology. And the patent and the field implementation was conducted later. But the whole approach here is that it is not a pure attached growth process. It is not a pure suspended growth process, but it's a hybrid technology, which brings us, the whole advantage of combining both here. So how we essentially did was that we had modules. Now these modules are nothing but the system for enabling the growth of bacteria on the surface. That is what they will encourage the attached growth process to happen. Then there is an aeration section where the oxygen gets introduced through the air, and there is a attached growth here, there is a suspended growth here, and finally there is an anoxic zone which basically gets some part of the recycle here, and the whole process essentially continues here. So one of the advantage that we clearly see here is that in the SBR technology, we need what you call as the decanters, which are an integral part of the whole system. So we have used the principle of gravity here and the natural displacement, basically to remove the whole concept of decanters here, and that's where the wares that are being provided here essentially will allow the clean water to come out with just a displacement mechanism, which also reduced quite a lot of cost from the whole system. So there are multiple advantages which we can see with the AGBR technology that got introduced with the systematic development that happened with both attached and the suspended growth process. Essentially, what it benefited us is in terms of reducing the power consumption against the conventional SBR process by 10%, and the footprint reduction we could achieve was 15%, and the sludge reduction, what we could clearly see, was close to the 20%. Which exactly what this country needs today, and that's where the technology essentially is now ready to deliver. So the patent was awarded for this technology, and then there was no much challenge to get this patent out, because it was a very novel idea with the hybrid technology in place, and it was granted within within a year of its application, which is quite fast. Now, finally, I wanted to conclude this talk with what we are trying to do as far as the L&T is concerned, and where essentially the engineers, and particularly the chemical engineers, can contribute more in the water domain. So this is the Water Technology Center that L&T is building at Kanchipuram, with a state-of-the-art facility as far as the microbiology, waste-to-value, membranes, hydraulics lab, analytical lab being set up there. We also have the pilot testing facility too. When we develop our concept in the unit operation lab, we can take those prototypes to pilot and then demonstrate the success of the technology through the pilot studies. So this is how the Water Technology Lab is being conceived, and the technology developments. We have identified series of technologies that we kind of need to bring into the water space in India, particularly, and that's where I wanted to, in fact, conclude my talk. So as we started this whole discussion, the role of chemical engineer is not just to progress today. So progress has happened, progress will continue to happen. Preserve is also another part, protect is also another part, which we got to start thinking. So both, you talk about land, air, or water, the focus has to be now deeper, and the impact has to come out now in terms of protecting and undoing the damage that has already happened to all the three resources. And particularly in the water, the opportunity is quite immense. Water domain has multiple challenges, because the sensors were getting the appropriate readings, be it BOD, COD, or the micropollutants, the metals, and then these are all very difficult. And when we want to understand the total quality of the water, the cost of testing is quite immense there. So chemical engineers have an immense role to play there, in order to develop new sensors, be it inferential, secondary, whatever you want to call it. But if you can come up with reliable sensors to, in fact, understand the quality of the water at very small trace impurity levels, that's a big change that we can bring to the society. Finally, the safer, cleaner, and enjoyable future is ahead of us, and then that has to be crafted by chemical engineers. And with that, I wanted to conclude my talk, and I will be happy to take any questions after this. Thank you, everyone.
Thank you for your insightful talk, sir. I hope our audience have actually found it very informative. And right now, we have a few questions on our YouTube channel.
Sure, yeah.
So I'll tell them to you. So one question is asked, which method of wastewater treatment is more efficient for industrial wastewater?
Okay, that's a difficult question because every wastewater is different. Let me try to answer it in a different way. Depends on what is there in the wastewater at the end of the day. If it is loaded with inorganics, then it may be just about removing those inorganics which do not require biological methods. But if it is also loaded with organics, then the concentration of the organics also play an important role. If the organics are biodegradable, then the kind of methods that are required is different. If they are non-biodegradable, which we call it as the recalcitrant organics, then the method of treatment is going to be different. If they are biodegradable and if they are in higher concentration, then we typically go for anaerobic treatment. If it is biodegradable with a lower concentration, we try to go with aerobic. Again, it has to be dealt case by case. Every industrial wastewater is different. What comes from the textile effluent is not same as what comes from the steel effluent. But between the steel industries also, there could be a lot of variations. So industry A and industry B of the steel making will have two different types of water coming out depending on the process they follow. So that way, that's where our knowledge becomes very, very relevant here in terms of understanding the water and of identifying the treatability part. And that comes with a lot of experience and expertise in the domain.
So, sir, would you suggest having a wastewater plant for each industry or combining them at localized areas?
Okay, that is a very important question here. Depends on, again, the situation that we have. If it is a small scale industry, then the governments, and they're mushroomed in a particular place, definitely government would like to have a CETP, that is centralized effluent treatment facility there. But doesn't mean that you can allow the industries to pump in all their waste into the line where the government owns the responsibility to treat it. So the whatever the discharge that has to come from a particular industry, even into a CETP, must be treated to some level where the burden of treatment at the CETP can be considerably brought down. So if the CETP is not available, and if it is or the industry is landlocked and something like that, then there are large scale industries are already treating it within their premises, and the reuse recycle is becoming a mantra everywhere nowadays with the industries now. So again, it depends on what's the situation and the regulation that they have to comply with.
Thank you, sir. There's one question in the chat which is, what soft sensing techniques are used in wastewater treatment?
Okay, that's a very interesting question and a great question. In fact, the soft sensing is quite prevalent in wastewater industry. And many techniques that we in fact use for sensing wastewater parameters are soft sensors in some way. I mean, we may not have an explicit MATLAB programming sitting outside to read the value and then give you the output, but there are inbuilt chips into every sensor now that is coming up and giving you appropriate reading. Let me take a very simple example. Talk about a TDS sensor. Now the TDS sensor, the measuring the TDS value in a lab is different. You know, you have to basically evaporate the water and understand the amount of solid that is now left after all the moisture is taken away. Now measure the volume of the water that was taken and the water, the things were collected, and then come up with the TDS measurement. But that's now it happens. What is read is conductivity. The conductivity is transferred to the TDS reading with some correlations. So when you see somebody dipping a sensor into the water and giving you TDS reading, he is essentially using the conductivity as the value to infer TDS here. So that is one kind of inferential system what people are doing. Now people are also trying to estimate a relation between the absorbance of UV versus COD. So when we talk about COD, it's a rigorous 2.5 hour to 3 hour test, which we need to do it in the lab with all the acids and then the other chemicals. But then people nowadays pass it through the online sensors, and then they say this is the COD. That is again based on the UV absorption capacity of the water and other parameters which they are soft sensing and giving you that reading. There are techniques that are now being used to convert COD to TOC for a particular kind of waste now. So TOC is a total organic carbon and COD is the chemical oxygen demand. So there is a relation for a particular wastewater which is being developed because TOC can be reliably measured online. And if you can infer COD through TOC, that's even better. So that's again a technique which people are coming up with, and the work is going on there. So there's a lot of machine learning and there's a lot of data analytics that is getting involved in terms of getting the reliable measurements.
Thank you, sir. And we have another question asked by Kaushik in the chat. Okay. How much time does it take to complete one cycle of treatment, and how can it be reduced?
Sorry, could you please repeat it again?
Yes. How much time does it take to complete one cycle of treatment? How can it be reduced?
Okay. I think what Kaushik actually means is for the SBR technology, if I am not wrong, because the cycle for treatment is essentially a concept for the SBR or a batch process, right? Typically we take about 3 to 4 hours as a cycle time. And we give maximum amount of time, or at least half of the time of the cycle we allot it to the aerobic process to happen. So we blow air and then we allow the carbon to carbon dioxide separation with the aerobic process. And then we give some amount of time to settle and then clarify and then allow the water to overflow into the decanter. So that's the typical cycle time what we talk about. And his question is very relevant if it is related to SBR. Yeah, it can be reduced further if we can bring in more bacterial concentration into the reactor. That means the MLSS in the reactor has to be high. The concentration of oxygen, if it can be improved further into the reactor, that's also another parameter which can accelerate the whole process. The nutrient removal mechanism has to be looked into, thoroughly. That can bring you some advantages into that. So we can in fact increase the oxygen transfer rate in the reactor because these are all done by the fine bubble diffusers and they have their own limitations. So if we can focus on that part, that is also another parameter which can give you some improvements. Number of factors are there, and we can definitely focus on some of the relevant things and the most dominant factors which can give you that benefit.
That answers your question, Kaushik. Okay. And Abhishek asks, what is the total cost incurred in this whole process? And please give some insight about the efficiency and yield.
Okay. So in which process?
This was asked some time ago. think it's right now not present in this.
Okay, fine. Yeah. Let me know in case if the question is clear, we can definitely take it up.
Okay.
Yeah, later point.
So, Sagnik asks, what are the wastewater treatment methods that can be carried out by individuals in their household?
Okay, yeah, that's a very interesting question. Yeah, that's a great question, in fact. So basically, if you see any apartment complex today, every big apartment complex has to follow what you call as the zero effluent discharge. I don't call it as a zero liquid discharge. We will call it as a zero effluent discharge. So what's the technology that they are using today? They are treating water inside the apartment complex to the extent that it is suitable for reuse. The reuse could be for the washroom applications, and the excess water, whatever you still have, can be used for the gardening purpose. So this is exactly what's happening in most of the big apartments complexes, and the government is mandating it in most of the states today. And when you look into that, the aerobic process, whatever we just talked about, the SBRs, the MBRs, MBBRs. So these are the technologies which are being used in the basement of the apartments, and they are essentially active to give you the water of the required quality, which you can use for gardening as well as the washrooms. So that is where zero effluent discharge is concerned. But many apartment complexes today are also looking into treating even the incoming water, that is what we derive from municipalities or from the bore wells. So there is some level of suspended solid removal that happens at the early stage. We remove hardness for the water so that we can easily use it in our geysers and other household applications for bathing and other stuff. So these all techniques are now coming very much in the apartment complex. But if we are talking about individual use and the individual houses here, yeah, we can think of this home RO system. That is also one way of treating the water, and whatever the discharge that comes out of this home water RO system, how we can probably make it more concentrated and only allow the salts to get separated rather than throwing the whole concentrated water back into the plants and other things. There can be technologies that can be looked into. So depends again on the size of the apartments, the size of the house, the nature of the complexes that we are thinking about.
Thank you. I have one more question. So as in right now, we have been discussing about all the treatment systems where you have sewage water into your plant. So what about rural areas where there's no proper sewage system in place? Or when you have to clean some large water body like a pond, a small pond.
Right. Yeah. So definitely, the pond cleaning will require us to look into the techniques that we have already talked about, which is aerobic process, and then cleaning with the membrane systems, and then removing certain impurities that are there either in the suspended form or in the dissolved form. So all these things are definitely applicable to the pond system. But if the question is related to rural areas, see why we are successfully able to treat water in urban areas, because we have a collection mechanism where the household discharges are being collected at one point, pumped to a treatment area, and then we have infrastructure there in place to treat the water. Now, if you want to talk about rural areas, we got to finally understand what is the collection mechanism that we should have. Of course, we have a basic septic tank as a concept in for ages now, but then even when the overflow comes in, so what is the collection mechanism you have? How do you basically need to converge everything into one stream and finally take it to a place to treat? That has to kind of be thought through and evolve with the time. Having individual houses to treat the water is not easy, and that's not safe also. So we got to think beyond the current method of treatments.
So I hope there's enough research happening in that area.
Absolutely, yeah.
Yes, sir. We have reached the end of the
Awesome.
questions
Yeah.
also.
Great.
So,
Yeah.
and thank you very much for coming to us event and also delivering an amazing lecture. And I believe that all our participants have found it very insightful and some of are inspired to continue research in this area.
Absolutely. Thanks, Manichandana, and thanks for coordinating this and organizing this. The questions were quite insightful. They were quite nice. And thanks for giving me this opportunity to talk.
Thank you, sir.
Bye. We can close the session now?
Yes.
Okay. Thank you.
Thank you.